Fiber optic cables lie at the core of modern communication, bringing us high-speed internet, video calls, and information transfer across continents and oceans. But how do these tiny glass or plastic strands carry vast amounts of data with such efficiency? The answer lies in the principle of total internal reflection, combined with some clever engineering. Let's start by examining the structure of a fiber optic cable. Each fiber optic cable is made up of 4 main components. At the heart of the fiber optic cable is the glass core, made from ultra-pure optical glass. This core is responsible for carrying light signals, making it the primary element for data transmission. The glass cladding is a layer surrounding the glass core, made from glass with a lower refractive index. Its purpose is to reflect the light signals back into the core using total internal reflection, ensuring the light stays confined and travels efficiently along the fiber without escaping. The primary buffer is a protective coating that encases the glass cladding and core. Its main function is to protect the delicate optical fiber from physical damage, moisture, and environmental stresses. This buffer helps prevent signal loss by shielding the fiber from bends that could impair performance. The outer jacket is the external layer of the fiber optic cable, made of durable materials such as plastic. It provides an additional level of protection against physical damage, abrasion, and environmental hazards. The outer jacket ensures the cable's structural integrity and can be adapted for various environments like indoor, outdoor, or underground use. Now, let's explore why the glass cladding is so essential. Its main function is to enable total internal reflection, ensuring that light continually bounces within the core as it travels long distances without leaking into the surrounding environment. Without the glass cladding, the light would lack a surface with a lower refractive index to reflect off, causing it to pass straight out through the sides of the glass core. Let's take a closer look at total internal reflection and how light moves through a cable. Picture shining a flashlight down a long, dark hallway. After a while, the light gets weaker and disappears. Now think of that hallway as a fiber cable. In fiber optics, to get light signals to travel without fading, we need the light to bend, or refract, at sharp angles, creating a zigzag pattern that moves it forward through the cable. When light reaches the edge of a material with a different density, like the cladding in a fiber optic cable, it bends. If the angle and materials are just right, the light bounces off the inside surface of the core and keeps moving forward instead of escaping. This bouncing is called total internal reflection. The angle at which the light hits the cladding is very important. If the angle is bigger than something called the critical angle, the light reflects back into the core. This keeps the light trapped inside, allowing fiber optic cables to carry it over long distances. If the angle is smaller than the critical angle, the light would refract and pass into the cladding and escape. That's why total internal reflection is essential for fiber optics to work. So how does this light carry data such as text, numbers, and even voice? Fiber optics transmit digital information in the form of binary code, a series of ones and zeros which represent instructions to the receiving device. But instead of manually sending strings of numbers, fiber optic systems use something called pulse code modulation. Here, the ones and zeros of binary code are replaced by pulses of light, similar to Morse code. A light pulse represents a 1, and an absence of light represents a 0. This flashing light signal travels through the fiber, allowing a computer on the other end to decode it back into text, audio, video, or any other form of data. Now let's delve into the type of light utilized in fiber optic cables. Not all light can be used. For instance, light from a bulb won't work. Fiber optics require light of specific wavelengths. The light we see daily is just a small fraction of the electromagnetic spectrum. Fiber optic systems use invisible infrared light, which has a longer wavelength than visible light. Infrared light is ideal because it experiences less signal loss or attenuation as it travels through the fiber, ensuring strong signal integrity even across long distances. Fiber optic cables are indispensable to modern telecommunications, seamlessly connecting cities, countries, and continents through high-speed underwater networks. They also revolutionize medicine, enabling precise internal imaging with endoscopes. This concludes our journey into the fascinating world of fiber optics and the physics driving this cutting-edge technology. We explored the structure of a fiber optic cable, emphasizing the vital role of cladding in achieving total internal reflection. Additionally, we examined how binary data is transmitted as light pulses and the advantages of using infrared light for its longer wavelengths and exceptional signal retention.